All right, so let's continue our algorithms course. So today we will talk about linear programming, which is its own thing. Basically, it's a class of optimization problems. And the good news for you today is not going to be very hard as far as trying to solve them, because it's a pretty well solved problem. So usually, again, as this is most things, if you encounter a linear programming problem, you can usually use a pre-existing library. But hopefully the goal today is to see how these algorithms work. Maybe to see the approach made by George Danzig in 1940s, how he came up with this idea. But let's first find out what are we trying to solve, right? So what in the world is this? So we are here. Linear programming right after midterm. Here I'll adjust it. So topic, I guess I'll call it topic 15, I guess. I don't know, something like that. Right. And there's of course a collab, and also the name is not correct. I guess it's just a quiz on linear programming quiz. I'll call it linear programming quiz. Okay. And George Danzig, of course, right? So let's go into this Colab. Let's see the site. Again, you can open it up here on a Colab, but this is actually linear programming here. So what I'll be doing, I'll be using a code space here from GitHub, and hopefully it works. Topics. Let's see if it works. So linear programming. What do you think? What kind of functions we're going to be working with?
Linear.
Yes, exactly. Yes. So, but it turns out many things you can reduce to linear problems. This optimization. So basically, this means is you have some constraints. You have a real world problem. You're trying to make some widgets, or you're trying to, you're running a factory, or you're running something, right? On or logistics company or something, and you want to optimize, you want to get, I don't know, most profit or maybe most time. There are different things you can optimize. Usually it's money, of course, but let's see here, where is our linear programming, where did I put it? Did I put it here? Yeah, for some reason I put it here. Okay, all right, because maybe I used different folder when I made it. So let's see, let's start kernel. Let's see if it's loaded. Yeah. And this notebook comes originally, I adjusted it, but it came from IBM actually, because they are offering this optimization service as a service, data as a service. Of course, you have IBM Cloud account and everything, right? So let's look at the introduction basically, right? So maximization, or also possibly minimization, right? Min or max, you have some function, right? And you have linear constraints, right? For now, all these variables are continuous, meaning, floating point, right? So objective constraints must consist of linear expressions, right? So a scalar product, right? So let's look at the real constraints. Maybe it could be constant constraint, like x has to be, 5, right? Could be some less or equal, or more than equal. Notice you're not allowed the strict inequality in linear constraints. So continuous variable, right? Is something that we don't know, right? So basically, restrictions variable should take integer values is currently not allowed, right? So this is all symbolic, right? So minimize something subject to these constraints. This is very generic, but let's look at some real examples, right? So let's look at these real things which are linear programs, which are not, right? So minimize the 2 times x and 5 times x, right? 5 times y, right? 2 variables, right? The names are not important, right? Of course, right? So that is a linear programming problem, right? How about this one? This is not a linear programming problem, because the variables are basically multiplied by each other, right? So some sort of quadratic thing. So not good. Same thing goes for log, right? So minimize or maximize, these are correct objective functions. This is what we're trying to find, the maximum value for this function, basically. So basically, in other words, we're talking about two-dimensional space here. So it only have 2 variables, right? To make things easy to learn. in real life you have maybe 100 variables, maybe 200 unknown variables. You try to maximize. You say, okay, basically saying, okay, which, basically in other words, what do I plug in x and y, right, or x, y, and z to maximize this, subject to these constraints. And in this case, it says, okay, 2 times x plus 5 times y must be less or equal to 7, right? So here, so basically you have to choose, what do you do, right? So this, in this case, of course, they're related here, right? So it's like very interesting, like, you know, whatever is less, right? So what is the x and y values here, right? You have probably many different choices here. If you only have single constraint, right? But usually there are other constraints. This also works, right? Same type, right? But this is not allowed, right? Because this is again quadratic, and this is because, of course, you have a strict inequality. Again, this is classical linear programming, right? So decision variables. Right? So basically, you can think of, actually, I would say this. You can think of it as other constraint, right? So basically, you say x actually, right? So this is an interesting point, right? You have this constraint. This is also, you can think of it as a constraint that x actually has to be -1 to 1 in this case, right? Some values, basically, right? Sometimes, of course, x could be maybe, 0, positive, typically positive values up to a certain point, right? And notice here again, it is not allowed to be just a discrete requirement. Those will be different type of problems with their own problems, so to say, yeah, with their own constraints. It's possible to have this type of problem, but it's not. We're not discussing it at the moment, not right now, right? So this is a classical linear programming issue. So typically this would be like a production problem, and here the the problem is this company. A phone company, I assume it's probably in China somewhere, right? Now these days, I don't know any company which makes phones these days, right? But the thing is, they're making desk phones and cellular phones, right? So these examples from like about 10 years ago, then this was still a kind of active. These days, well, I would say they're mostly making cell phones, right? Desk phones, well, I suppose they could be making some sort of network phones for companies. Now, let's just imagine, right? Because how many people have a desk phone at home? Anyone actually have? The parents have, the grandparents have.
My grandmother has.
Your grandmother still has it. Good for her, right? Yes. So you can call her up, right, if she can pick up the phone.
This.
Yes. I'm actually seriously questioning. I have my mother. She doesn't want to use technology. We actually try. I'm going to set up her network phone, but it's going to look like a regular handset, basically. And it turns out it's really hard to find a regular handheld, regular phone. 5 years ago, it was relatively easy. Now everybody has thrown them out, right? Yes.
Well, I just sold the one like a week ago. I found it in my attic and.
Well, don't come to me. I have bought it, right? How much did you sell it for?
€5.
Yeah, that's what I'm paying. That's what I'm paying. I guess I'll have to go up to €10, right? So you guys want to have a phone? I'm seriously in the market. No joke for next week, right? €10, right? So. You have iPhone in attic, right? But not the really old one. That's too old. No, just a regular push button from 10 years ago is fine, right?
10 euros in good grade.
Yes. Seriously, yeah, you find one. But yeah, because I have the router, and because the network routers, you can buy a router which actually takes a phone. And also, if you look at the mobile routers, right? They also have a phone jack actually, right? You check like from LNT or Vite, right? They also have a jack. You can still do it theoretically, right? In old days, this was kind of maybe 5-10 years ago. There was some reason for keeping this phone, right? Because if power goes out, phone network was separate because it was copper-based on its own power source, like 18 volts or something like that, right? And so theoretically it makes sense. Yeah, there's no power, there's no internet, and you have a phone which should be working, but it's separate. But these days, as far as security goes, it's not really worth it because your power goes out. How should I say? You are, out of luck. SOL, right? In any case, right? So, okay, but yeah, let's go back to this example. But okay, so let's imagine, they're still making desk phones. Good for them, right? But they're making two. They're assembling them, right? So it's full service company painting them, right? So objective is maximize profit, right? But there are also some goals, right? What they call them these days in the business, management is KPI, right? Key performance indicators, right? They need at least 100, right? Of phones, I guess. There's some sort of, I don't know, agreement or something, right? So again, this is, of course, very simple example, but in real life, that's what happens. You have some things which are not, you can't just say, okay, cell phones give us most money, let's just build cell phones. You need some legacy desk phones. So basically, you need to write a model. You have to write this descriptive model. What's what you're trying to do, a mathematical model, right? So what's decision variables, right? So decision variables will be how many phones you can build. So we can call them, I don't know, D or C, or I don't know what they call them here, right? So decision variables is how many desk phones, desk production. Again, I guess this could be a variable, right? Desk production, right? And also, cell production, again. So that's a variable, right? So, but you have a bunch of constraints. So desk production should be greater or equal to 100. Cell production should be greater or equal to 100, right? And also, assembly time for desk production plus assembly time for cell production should not exceed 400 hours. Maybe there's some worker rights or something, right? You cannot, basically don't have enough workers, right? So no more than 400 hours. And painting time, no, I don't know, it seems like a lot of time to spend painting them, right? So cell production, okay, so cell phones, right? Okay, plus desk assembly. So both of the, so you have basically limited time of assembly. So what is that? 40 hours. That's what? God, is that in a month? For what was it in a week? No, 400 hours. That is what? That's like, I guess they combine how many hours? I guess it's it's not just one worker, right? Of course, right? So 490 hours. Maybe they have 10 workers or something. Okay, so 400. So those are the constraints, right? But the thing is, what's interesting here about this model, which if you think about it, I'll make this a little bit bigger so you can read this, is actually, it's kind of breaking its own promise of the restriction, right? Which one, if you think about it, it's this part here, right? Because classical linear programming, you are allowed what kind of values? Floating point, basically, right? But if you think about like making 105.6 phones, like how meaningful that is, right? I guess you could say, okay, yeah, the 0.6 phone is like goes into next month's production, the rest of 0.4, right? So it's like that exercise about the city, right? How people, like, do you have 1,500 and 0.6 people? What does it mean? Like, so again, so some things again are not completely, as usual with these modeling exercises, all models are wrong, right? But, hopefully some of them are somewhat useful, right? So we convert this to a mathematical model, right? So use decision variables, desk precision, cell production, right? What we have, we basically want to write these formulas. And again, hopefully these are all linear, right? On domain of decision variables, right? So maximize, and again, where is this 12 desk production plus 20 cell production? I guess those are prices. Let's see, where do they come from? Actually, 12 on 200, 12 on 20. Because I guess it must have come from something. So 100, right? So this is okay. So at least 100 each. That makes sense. Also, this is the actual time spent, 0.2 times desk production plus 0.4 cell production, right? So this is how many hours. Okay, yeah. All right. So this is how many hours are spent on assembly, right? Apparently, painting desk phones is kind of long. So let me put some notes here, right? So notes. Apparent. So maximize is in maximize function. So in maximize function, well, is price we get from desk phone, and 20 is price we get for cell phone. Yeah, cheap cell phones, really, €20. I don't know, whatever, 20 yuan or $20 cell phone, right? But I guess again, if it's for mass market, right? Maybe it is, right? But again, these are just I don't know, maybe gold pieces. Right, so, but 0.2 and 0.4, so again 0.2 hours is how much times is spent on desk, on assembly for desk phones, right? 0.4 hours is for assembly of one cell phone, right? That's like, what is that, 0.4 hours, that's 24 minutes. That's possible, I guess, right? And painting, I don't know, I thought robots would be painting the phone, but I guess not. 0.4 hours, so that's half an hour for painting each desk phone, right? That seems a lot. I would just dunk it in the paint or something, I don't know. Right, and hours for painting each cell phone. But again, this is like the IBM made this like 10 years ago, so we'll go for this data, right? So maybe I should put this here. I'll put some little stars here. Makes sense. And of course, when you're building this type of problem, right? It's of course crucial to get the formulas right. So now, of course, we will look at how we would solve this using a Python library, and only then we will look at how we would solve if we didn't have a library, right? So library is pretty easy. The hard part is actually that's what actually would happen in real life. You have to come up with these constraints, and then you figure out some software, right? It could be Python library like we will be using here, but it could be some software packages, right, which let you just enter values, right? So the formulas on probably ChatGPT could do some of it, but probably not all of it, right? This problem, right, and try to solve it for us, basically, right? So here we'll use Docplex library, which so happens to be built by IBM, but it's open source, so we can use it, right? So of course we will need to download the library because I'm almost certainly sure, right? I'm going to draw the, let's see, we have code space linear programming, right? We don't have any, what's our CPU here? Let's take a look. General Intel, 837C, they're on Platinum, right? Okay, that's good, 2.8 gigahertz, that's very nice. All good stuff, but what's my username? Azure. Okay, so I'm somewhere on Azure Microsoft servers somewhere, where I don't know. But that's my Python. It's probably 3.10, I would imagine. I hope so still. Speaking of Python, 3.13 came out like a couple of weeks ago, like 2 weeks ago or 10 days ago. But there's no need to rush because all the big libraries have not yet migrated. So now, what we'll do is here, we are going to try to import Cplex, right? This means we have it, we try it, right, as you all know, and if there's a prefix, right, we are in virtual environment, pip install, else we install Cplex or pip install user Cplex. Let's see which one we use, right? And maybe we'll do this here. Print, we can do print here. Print. We are in virtual environment. Oh, good. We are in container. No, we are not. I don't know. This is kind of no AI. Let's see what happens here. I don't know if this is this going to work if I do this. Let's see. Let's see if this works. Okay, now we'll take a look. User and Cplex. Let's take a look what happens. Installing for user. Okay, let's take a look which one works. Or will it work? Okay. So this actually this didn't work actually. So I guess we'll do this basically, right? So basically, I'm going to skip this part here. I'm just going to install it globally, right? For this check didn't work, we will, installing globally, print it, installing globally, yeah. All right, but of course globally we are in a container, so we don't care about it, right? So we are fine. Let's take a look if this works. Oh, wow! It doesn't. Oh no, it did not find it actually. That's very interesting. Because I wonder why I didn't find it. Because we have it here. I believe we are on conda. Let's take a look again. So I would like to install this. Let's see. Pip list, right? Do we have anything good? We have a bunch of stuff. So what's happening here? If pip install Cplex, what happens here? Oh, very interesting. Why didn't I find any more? Because it's available. Won't be able to. I'll have to go to Colab then. Because it worked before. To go to PyPy, right? Or of course, you go to Cplex, right? It's active package. April 3rd, right? There's a whole bunch of maintainers, right? It's a community library, basically, right? Of course, IBM is the creator, but it's still open source. So why doesn't it work? Pip install Cplex. Maybe conda install Cplex. Can we do that? Conda install Cplex. Let's take a look. Yeah, there's a package here. Can we do this? This is 6 months ago, 222. Yeah. Let's try this one. I'm just going to leave it dangerously, of course. If not, I'll just come on. Hello. Yeah. Okay. Not Control Z. I'm lazy. Is this going to work? Oh, that's my file. Okay. What doesn't like? So there's some sort of is installed 3.5. Are they like really? Let's double check this. Is this really stupid or they want Python 3.6 for some reason? I don't know why. There's some weird. I know I've installed before with no problems before. Maybe I might need to just look at the pretty pictures and not actually do any work, right? Unfortunately, or I'll have to go to Colab then, which used to work before, right? Pip install Cplex, right? It's interesting why it wouldn't work. Let's try this one more time. What did it say? Let's do R pip install Cplex and could not find a version besides report Cplex. What's from versions none? Huh. Interesting. Yeah, I'll do this during the break. I'll check. Okay, let's go. So yeah, we can see again you have installation problems, right? So you basically create a model, you get an object, right? Import the model, and then you make a name for it, right? And you set up a desk variable. That's what we are trying to find. Desk and cell. Come up with your variable names, right? Type, and of course, you set the constraints, right? You need at least 100 desk phones, cell phones, right? And then they have this library has pretty nice syntax. You just say, okay, these are the constraints, right? You enter these linear formulas as a parameters, right? It works pretty well actually, right? So 0.2 times desk plus 0.4 times cell, at least less or equal 400, right? So less or equal 490, right? And now we want, this is our maximize, this is our formula that we want trying to solve, basically, right? So, we can print it, right? These are the constraints, and then we can solve it. But before we can solve it, right, let's look at the graphical representation. So this is what we have, actually. So, we have two variables, right? X and Y. In this case, our cell are C and D, cell are desk, right? We're trying to maximize. On this area, notice here, we have this lower area, right? We cannot do, less than 100. So these two fixed lines, they sort of give us a lower bound. And the upper bound is given by these other lines, right? So we have basically 4 lines which present us with a set of, potential infinite, solutions, variations, X, 105.6 cell phones and 108 desktop phones somewhere here, right? So now, how we can see this graphically, if we only have 2 variables, it's pretty easy to visualize. The problem, of course, is usually you have more than 2 variables. You have like this multi-dimensional space, you can't visualize it, right? But the same principle applies. So the beauty of this is, of course, that what is George Danzig, I should show you with his example, right? He found that, and this might seem like kind of like obvious idea. You're trying to maximize this formula, right? There's some line you're trying to maximize, right? Maybe we'll see it here. So this is the solution we're trying to maximize. This line, right? 12 times D plus 20 times C, right? So notice something here, right? So this is a line you're trying to maximize, right? And the thing is, what he found in 1947 is that the solution, what's the requirement for solution? The optimal solution is where? It is,
Cross point.
yeah, it is at cross point. Not only, we'll see, it's not the only recommended, but basically, the actual optimal solution must necessarily lie on the edges somewhere, right? Usually on a, how should I say, cross points, yeah, I guess we'll call them cross points, right? But, so basically this means you don't need to look all those here. So you can solve extremely complex problems, assuming they're all linear, right? You don't have any problems. Basically, imagine this multi-dimensional, I don't know, sort of like a, I don't know, in 3 dimensions be like a ball, like, or some sort of like, I don't know, what you call it, some figure, right? But you just have to look outside. You don't have to go inside, basically, right? So there are ways of doing this, actually, right? And it will work. There are some algorithms which will basically work pretty well, even for very complex situations. So that's basically what we are trying to solve. And you could do this again, even before computers. You could do this pen and paper for some simpler problems, right? You could solve this using a pen and paper and could figure this out. So optimal solution actually turns out to be 300 desk phones and 850 cell phones. You could calculate this. So what is that? 3,600 money, profit for the desk phones, and 20 times 850 is 17,000, so that's 20,600 together. Yeah, that works. Okay, yeah. Just sanity check, this actually is correct, right? You can never trust all slides. So, now, so again, all solutions along this line yield. So basically, this is our winning the formula, right? This is the winning this is winning line, but only one point lies on our cross here. So if you think about it, it's possible to have also infinite solutions. How is that possible? If this line happens to be exactly as a bounding line, right? Then you have multiple solutions actually. In this case, the slopes are different, right? So actually the solution is just unique, right? It's possible to have multiple solutions, right? So, so 12 desks, right? So the answer is 300, 850, so you can give to your manager, okay, this is what you do, right? Again, so this will work, assuming your constraints actually remain in place, right? You make 300 desk phones and 850 cell phones, and in this case it's also very convenient because we have nice continuous, our continuous values, answers actually integers here.
I have a question.
Yes?
Do the most optimal solutions also include the cross points, such as at the point 0? Yeah.
This one and this one? Yeah. Well, the thing is, okay, it is possible, right? It is possible, if you think about if the slope of this solution line would be different, right? It's possible you can hit this would be the solution. It's also possible this one. It's also possible, there will be in a slide later on, that we actually have all of these are solutions. It's possible to have all these solutions sometimes, right? Yeah. But in this particular case, so the answer is fine, was that we have to check, these are the where we have to check, right? These cross points are very important, basically, right? So you basically need to check these cross points for all these different functions. Yeah, so really works really well. Yeah. Okay, before we go to break, I want to talk more about George Danzig. I think I have some information about him. He's pretty famous. He only actually died very recently, right? But there's a story on Snopes, right? Consent. You've probably seen the movie Good Will Hunting and some other ones, right? It's the famous story, which I think we all would love to see. It's a story of student who comes in late, sees some problems on a board.
It was about the statistical problem.
Yes, and that's the guy. This is the guy who solved this linear problem. This is the guy, George Danzig. He is the one who solved this. So basically, when he did this, he was actually studying for PhD, I believe, actually in real life. And he came in late, and there were like 3 problems. And they seemed harder than usual, homework problems, right? And like 2 or 3 weeks, he gave him like 2 weeks, took him 2 weeks. He turned them in to the professor. Professor has a big stack of papers, he puts them in, but like a month later he comes, in the middle of, I don't know, a morning or something, the professor says, okay, hey, you solved these 2 unsolved problems, right? Basically, your PhD is done, basically. Here, you can publish these later on, so sometimes it pays him to come in late a little bit, right? But, so, So he got, because usually, of course, you have homework, and he had some extra problems, right? So it is a true story, right? And of course, during the George Danzig, right? Yeah, it is the 39 in Berkeley, right? It is a graduate level statistics class, right? So, but again, this story has been keep going, right? Yeah. And Sunday morning, the professor came 8 o'clock, right in the morning, right? Yeah. And so, yeah, so it came out pretty nice, right, for him. But he did a lot of optimization. He's pretty famous, like I said. So the point, of course, is if you don't know it cannot be done, maybe you can do it, right? Right, George Danzig. So let's see, he lived a pretty long life, up to almost like 90 years, something. And this guy here, he looks like a statistician, right, to me, right? He got the presidential medal and so on, right? So simplex algorithm, that's what we're talking about right now for linear programming, but he did also a lot of other statistical work, right? So he was not a programmer, right? Yeah. So yeah, and of course famous against this, right? So yeah, he lived almost like 90 years, right? So Stanford University and so on and so on and so on, right? So yeah. So sometimes it comes in to not know that the problem is hard, right? And it kind of doesn't limit you. All right, let's take a break. Let's continue until like 12:10. 12:10? Yeah, so only 12:10, and then 1 second.